Hello, and welcome to the course of learning the basics of CNC programming. Before getting to know what this course contains, let's understand why learning CNC programming, or at least having a brief knowledge of the same, is very much requisite in the current scenario. One of the most exciting aspects of pursuing a career in the CNC industry is the job outlook. Currently, there is a skill gap, which has led to a high demand for machinists and programmers. So much is made with CNC machines, and there are so many industries you can get into. The manufacturing industry relies heavily on computer numerical control, or CNC machining, including operations that once used engineer operated equipments like routers, shaping machines, vertical millers, and center lathes. Manufacturers of many types across many industries choose the advantages of CNC machining for their fabrication and manufacturing applications. It provides efficient, expedient, and precise production capacity ideal for creating large quantities of items. The course will start with a basic introduction about numerical control, its history, and how it had been introduced in the modern industry. Then we will discuss about various types of popular CNC machines in the industry. And finally, we will learn about the basics of CNC programming, which will include programming format, explaining different types of codes such as G code, M code, S, D, F, and many more. Then we will get to know the most simplest and precise way of writing a CNC program with complete coding. Then we will discuss about two popular approach in CNC programming, that is absolute and incremental mode. And finally, we will write a complete program involving everything we have learned and even more. I hope this course helps you understand the basics of CNC programming and make you industry ready. For many years, machine tools have been operated by skilled machinists. Judgment about their speed, tool configuration, feed rate, and anything else related to the machine was done by the machinist. The quality of the product machined depended upon the machinist's craftsmanship, knowledge, and skills. It was almost impossible for two different operators to produce identical products. In fact, even one operator cannot produce identical products successfully. The complex shapes of aircraft industry and automotive industry were not at all possible by manual methods. It all changed during a machine tool exhibition in Chicago in 1960, where almost 100 plus numerically controlled machines or NC machines were displayed, which gathered attention of many industrialists of that time, and NC machines became part of our manufacturing sector. Numerical control of machine tools may be defined as a method of automation of various functions of machine tools by a tape-coded program consisting of precise instructions about methodology and movements in the form of letters, numbers, and sometimes special symbols. These programs are generated manually. Understanding about NC systems is very much precise because they are a milestone in the Industry 4.0 journey. So let's briefly understand the NC system by understanding the steps involved in an NC system. The first step is a part drawing. A part drawing is made or manufacturing notes are prepared for giving dimensions and specification of product to be manufactured. And in the next step, as per as the part drawing or the manufacturing notes, a program is written. In the next step, there comes a device called tape punch, which is a form of data storage that consists of a long strip of paper in which holes are punched. This tape punch converts the written program of the part drawing in form of instructions into hole patterns. In the next step, another device called tape reader comes, which reads the hole pattern generated by the tape punch and converts the instructions to a corresponding electrical signal. In the next step, a controller receives the electrical signal sent by the tape reader and sends corresponding instructions to CNC machine. And finally, the CNC machine responds to the signal from the controller and performs the required motions like spindle rotation, table or spindle movement, and many more. The CNC machine has an added feature of an onboard computer called Machine Control Unit or MCU in short. The machine functions are coded into the computer ROM at the time of manufacture, and they do not get erased when the machine is turned off. The MCU has a keyboard for manual data input or MDI of part program. Such programs are stored in random access memory or RAM of the computer. They can be played back, edited, and processed by the control unit. MCU also has a graphic screen in which the program and the generated tool path can be displayed. CNC controls are also referred to as soft-wired NC system because most of their control functions are implemented by the control software programs. CNC machines can be used continuously and only need to be switched off for occasional maintenance. These machines require less skilled people to operate, unlike manual lathe or milling machines. CNC machines can be updated by improving the software used to drive the machines. Training for such type of CNC machines can be done through the use of virtual software and simulators like CAD/CAM, Fanuc CNC machining simulation, Autodesk CNC machining, and Power Mill, and many more. The main components of CNC are part program, input device for part program, machine control unit or MCU, drive system, machine tool, feedback system, and display unit, in which the part program is a sequence of instructions which describe the work which has to be done on a part in the form required by a computer under the control of Computer Numerical Control software or CNC software. It is the task of preparing a program sheet from a drawing sheet. The next component is the input device for the part program. These are the devices which are used to input the part program in the CNC machine. There are three commonly used input devices, and these are punch tape reader, magnetic tape reader, and computer via RS-232C communication. It reads the coded instruction fed into it. It decodes the coded instruction and makes the CNC machine understand it. The next component is the MCU or the machine control unit. As we have discussed earlier, it generates, stores and processes CNC programs. It also contains machine motion controller in the form of executive software. The next component is the drive system. See, the basic function of a CNC machine is to provide automatic and precise motion control to its elements, such as work table, tool spindle, and many more. Drives are used to provide such kind of controlled motion to the elements of a CNC machine tool. A drive system or servo control consists of drive motors and ball-led screws. The control unit sends the amplified control signals to actuate drive motors, which in turn rotate the ball-lead screws to position the machine or cause rotation of the spindle. The next component is the most important component of CNC machine, that is the machine tool itself. It is capable to respond to the signals from the MCU and perform the desired operation for the manufacturing of the part. The next component is the feedback system. Feedback devices are that devices which sends the information back to the controller in closed loop system. This kind of feedback system or this kind of feedback devices we are going to discuss later on in this course when we are going to discuss about closed loop system. And last but not the least, we have display unit. The display unit serves as an interactive device between the machine and the operator. When the machine is running, the display unit displays the present status, such as the position of the machine slide, the spindle RPM, the feed rate, the part program, and many more. Now, let's discuss about different types of CNC machines. The first being point-to-point CNC machine. These types of CNC machines are based on motion. They are also known as continuous path CNC machines. In this system, the tool and workpiece are held at a particular location, while the tool does the operation like drilling, for instance. After the completion of the operation, the tool or the workpiece is moved to the next position of operation. The cycle is repeated until all the operations are completed. In this system, the feed rate and the speed of cutting tool or workpiece has no effect on machining process, unlike traditional machining methods. The dimensional information to be given to the machine are a series of positions of the slides of the tool or workpiece. So basically, a starting point and the next point is required for the process. Now for instance, if 4 holes are to be made, the program would simply specify 4 points in between the starting and next point, like 1, 2, 3 and 4 as shown in the figure, and the machine tool will perform the requisite drilling operation. The servo system moves the slides to the position and no slide movements occurs until the cutter has retracted back. The machine using the system are drilling, boring and tapping machines. In this system, while the cutting operation is in progress, The slides of tool or workpiece move continuously to generate angular surfaces, 2D curves or 3D contours. Milling machine adopt this system pretty well. Next we have incremental and absolute CNC machines. Let's discuss about incremental system first. In this system, the distances are measured from one point to the next point. The movement from point, let's say A, whose coordinates are 2, 3, to the point B, whose coordinate is 6, 8, is specified by x is equal to 4, y is equal to 5. Now, for drilling 5 holes at 5 different locations, the command for x direction would be 500 plus 200 plus 600 minus 300 minus 700 and minus 300. The main advantage of this system is that inspection of the program is simple because the sum of commands for each axis must be 0. A non-zero sum indicates an error. Also, the mirror image programming is easy. It involves only the change of the signs of the command. Next we have absolute system. In this system, the movement command are with reference to the origin. The movement from point A to point B is specified as x is equal to 6 and y is equal to 8. Now for drilling 5 holes in this type of system at different locations, the command for x direction would be 500 plus 700 plus 1000 plus 1300 and plus 300. The main advantage of this system is that interruptions caused by tool breakage or tool change or checking the parts do not affect the position at the interruption. Also, dimensional data can be changed very easily. The next type of CNC machine is the open and closed control loop machines. Let's discuss about open loop system first. Here, the command for movement of the slides are given to the stepper motor. Now this stepper motor is a DC motor that moves in discrete steps. They have multiple coils that are organized in groups called phases. By energizing each phase in sequence, the motor will rotate one step at a time. With a computer-controlled stepping, you can achieve very precise positioning and speed control. For each signal in the CNC machine, the stepper motor moves by a fixed angle and causes a fixed movement of the slide. The command determines the amount of movement of the tool or the workpiece. There is no surety that the correct position is reached. Any possible error cannot be detected and corrected. The load torque due to cutting forces, the backlash in the lead screw, may cause error in the actual position reached. Hence, this system is more suited for cases with no resisting force. The next system is the closed loop system. The closed loop system is provided with a feedback system. The feedback loop gives the information about the error in the position reached. The input device compares this data with desired data and the corrective action is taken. The correct signal to the servo motor ensures that the position is reached. There is one more type of classification for CNC machine. that is based upon axis. Let's discuss about 2 and 3 axis CNC machines. 2 axis machines have movements along 2 axes, as in lathe. The saddle moves longitudinally along the bed and cross slide moves transversely on the saddle. In 3 axis machine, there is a motion along the vertical direction of the table, as in milling machines. In 3 axis machines, there will be one more axis, perpendicular to the above 2 axes. By the simultaneous control of all the 3 axes, complex surfaces can be machined. A milling CNC is the best example of the same. The motion, or to be specific, the rotation of a spindle, can be found out by using right hand rule, which says that if you curl the fingers of your right hand around with the direction of the rotational motion, your thumb will point in the direction of rotation. Milling CNC centers have 2 more motions in addition to the XYZ motions: the rotary motion of the spindle and the rotary motion of the index table. Such machinery is what we call a higher axis machine. The 5-axis milling center is a more popular version. The real value of CNC can be found within higher axis machining. This is such a method that can never be accomplished by manual means. There are many advantages of higher axis machining, like reduced cycle time by machining complex components using a single setup. In addition to time saving, improved accuracy can also be achieved as positioning errors between setups are eliminated. Improved surface finish and tool life by tilting the tool to maintain optimum tool to part contact all the times. Improved access to undercuts and deep pockets. By tilting the tool can be made normal to the work surface, and the errors may be reduced as the major component of cutting force will be along the tool axis. This higher axis machining has been widely used for machining sculpture surfaces in aerospace and automobile industry.